Thanks for watching my video today. Let's see another infinite series of zeta function. This is general, okay? Generalize. So sum from n equal to 1 to infinity of zeta of 2n minus 1 into 2 to the t to the 2n, okay? Which is equal to t square upon t square minus 1 plus 1 upon 2 1 minus pi t cot pi t, where t is not equal to 0, okay? If t is equal to 0, then or this sum will be a divergence, okay? Divergence. Now let's go to our proof. Now let or this sum to be s, okay? S is equal to sum from n equal 1 to infinity zeta of 2n minus 1 t to the 2n, okay? Which is sum from n equal to 1 to infinity of zeta function, okay? Zeta function is nothing but sum from k equal to 1 to infinity 1 over k to the 2n, okay? Minus 1 t to the 2n. Now taking separately, now s equal to sum from n equal to 1 to infinity sum from k equal to 1 to infinity 1 over k to the 2n into t to the 2n minus sum from n equal to 1 to infinity t to the 2n, okay? This and this one, multiply it, which is same as sum from. Now these two summation, let's interchange them. Sum from k equal 1 to infinity sum from n equal 1 to infinity t upon k. Here if you see here, their power is same, so t upon k to the power 2n minus sum from n equal to 1 to infinity t to the 2n, okay? Now let's see these two summation, this and this, okay? Let's see these two summation. Now sum from n equal to 1 to infinity t upon k to the power 2n is nothing but, if you expand this summation, you get t by k whole square plus t by k whole 4 plus t by k to the power 6 plus and so on. And if you see this carefully, this is nothing but or GP, right? Geometric progression, which common ratio is to be t over k whole square, okay? Their common ratio is t upon k whole square. So if you use the formula for GP, then you get a times a is nothing but first term, this first term, t by k whole square upon 1 minus common ratio is nothing but t by k whole square, okay? If you simplify this, you will get t square upon k square minus t square. And again, let's see for this sum from n equal to 1 to infinity t to the 2n is nothing but, if you expand this sum, t square plus t4 plus t6 plus and so on. And again, if you see this is also GP with common ratio of t square, okay? Therefore first term then is t square upon 1 minus common ratio, which is t square. So let's come back to our summations s. So s equal to sum from k equal to 1 to infinity, and this sum is nothing but this one, right? Which is t square upon k square minus t square minus this minus, and this sum is nothing but t square upon 1 minus t square upon 1 minus t square. Now I don't want this negative sign, so this one this one if you multiply by negative, then you get, which is equal to t square upon t square minus 1, right? Which is plus, here is plus. So let me take 1 by 2 common here. 1 by 2 sum from k equal to 1 to infinity. Here there is no 1 by 2 here, right? So in order to be satisfied the order one, this one, so I'm going to multiply by 2 t square upon k square minus t square, such that these two will get cancelled, then you will get back this one. Why did we do this so? Okay, you will see here. So t square upon t square minus 1 plus, now let me take out t here common, okay? T square, right? This is t square, so I'm going to take out 1t. So t sum from k equal to 1 to infinity, if you take out 1t, then you get 2t upon k square minus t square, right? Now let's add and subtract 1 over t both, okay? 1 over t minus 1 over t plus 1 over t. Now which is s equal to t square upon t square minus 1 plus t by 2. Now let me write this first, 1 over t minus, in this two I'm going to take minus common, so minus, if you take minus common, so 1 over t, this will be minus, right? Minus sum from k equal to 1 to infinity 2t upon k square minus t square. Now we are going to see this summation, okay, this part. So in order to see this, now let's look at code, okay. Partial fraction expansion of code x, then is code x is nothing but 1 over x plus 2 times sum from k equal to 1 to infinity x upon x square minus pi square k square, right? If you see it's 1 over x, so this is 1 minus these two, I can interchange them, okay. 2 times, this is 2 times x is t, and x square, this one t square is pi square k square, right? We can do something here. Now if you substitute x equal to pi t, we have code pi t is 1 over pi t plus 2 times sum from k equal to 1 to infinity pi t upon pi square t square minus pi square k square, okay. Substitute x equal to pi t, then we will get pi square t square minus pi square k square, right? Here pi square common, right? Therefore you will get code pi t is nothing but 1 over pi t plus, now this one here, pi is in the numerator and pi square can be common, right, in the denominator, then you will get cancel, then we are left with 1 pi, so which is 2 over pi sum from k equal to 1 to infinity t upon t square minus k square. So if you look at this two, this is similar now, right? Now here if you see here, for this two, in the denominator there is pi, right? So this one we can transfer in here, so pi code pi t is equal to 1 over t, and this one, this minus, okay, interchange this two, then you get minus sum from k equal to 1 to infinity 2t upon, if you interchange this two, and or if you common this negative, so negative k square upon t square, so right. If you see this part, this is same as this one, right? So we nearly get our result now. Now let me continue in here. Therefore s is nothing but t square upon, so let's come to our s is nothing but t square upon t square minus 1, right, plus t by 2 times 1 upon t, this one 1 upon t, minus, and this summation part is nothing but this one, right? This is nothing but this part, so you need to be pi code pi t, and you get s is equal to t square upon t square minus 1 plus 1. Now t entering here 1 by t times, if you enter here, this t and t cancel, so 1 minus pi times t, right? Pi t code pi t. So which is our result now, right? This one. So here it is. So you get, therefore our sum from n equal to 1 to infinity zeta of 2n minus 1 t to the 2n is equal to t square upon t square minus 1 plus half times 1 minus pi t code pi t. So then is the proof for this infinite series, okay.